2.2, day 2. So this is still limits involving infinity, okay? And the only thing I might not get to is a little trick that our book offers called seeing the limit. Seeing the limit at infinity. We might not get to it. It's just a little trick. I can show it to you anytime I need to for the AP test. So, or even during Q&A. But our goal today is to talk about functions where we're not doing the limit, like LIM x goes to infinity. We're doing like LIM x goes to 2 or whatever, and the answer is infinity. Okay, so yesterday the infinity was in the question, and tonight infinity will be in the answer. Does that make sense? All right, so let's take a look at just a basic graph here. Let's say you had this function. There's this vertical asymptote, okay? And let's say the function looks something like this. I might be curious, basically, what the graph's behavior is near that vertical asymptote, okay? So this is x equals -2, where I have the vertical asymptote. So what would have happened if I asked you, what is the limit on the left side of -2? Okay, so yeah, what that means is you're looking at this arrowhead down here, okay, and you're asking, what is it doing, right? I'm on the left side of -2. What's going on here? My graph is headed down to the abyss, right? Or in Greek we call it the abuso. So, down, 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 down. Negative infinity it is. Negative infinity. And we can write equals negative infinity. All right. How about the right side of that asymptote? So if you were doing -2 from the right, now you'd be looking at basically this arrowhead up here, see? What's it doing on the right side of the asymptote, see? So what's my answer there? That one's heading up to infinity, right? Okay, so you can see here that you can get differing behavior, one on each side, right? Now, did you need the function given to you to answer that question? No, not really. All right. I will give you the function now. This function is f of x equals negative x plus 1 over x plus 2. Why is that? Well, there's a root at -1. See the x-intercept right there? That's why the numerator is x plus 1. And there's a vertical asymptote at -2. That's why the denominator says x plus 2. Just a little bit of view there. The minus, the reason it's got a minus there is because it didn't do the upside down. So we're actually going to do the upside down version of this now. All right, let's go on to the next example. So that would be like example 1. See how the answers came out to infinity? And negative infinity, like that? Okay, let's go to the next one. Same basic picture, only this time it's going to be sort of reversed. Still have an asymptote here at -2. This time it's this branch and this branch. Okay? And let's say we're asked the same two questions. Same two questions. So what is the limit on the left side of -2? So on that one, we're looking at this arrowhead. And what's it doing? It's going to infinity, right? Sorry, it's this graph, okay? It changes pages on me every now and then. All right, so it's going up to infinity on the left this time. And this time on the right of -2, it's headed down, right? So you're looking at this arrowhead. It's infinity, negative infinity, going down, down, down. Okay, so so we can see these are also limits involving infinity. It's just that the answers are infinity. And we're actually limiting that as 0, 1, 2, negative 2. So if you care to guess what this function would be, it is the upside down version of the last one. Anyone care to guess what my function is? Yeah, positive x plus 1 over x plus 2. Just drop that minus sign, it flips the graph over, right? So I'm just throwing in a little pre-calc review. Okay, there it is. That's not an answer, I circled it. Alright. Just seeing if you could guess my function. Alright, so what exactly is a vertical asymptote? Can someone tell me what a vertical asymptote is in words? What is it? What is a vertical asymptote? Yes. Okay. It's a restriction on the domain. It certainly is. You cannot graph through an asymptote, right? Not a vertical one. Unless it's a piecewise function, so it tells you a plot point line. I think we can answer that question with limits. Okay? So if you look back in yesterday's notes, we had a statement very similar to this one. It was like the line y equals b is a horizontal asymptote if either limit as x goes to infinity of f of x is b, or if limit as x goes to negative infinity is b. Well, we can write something similar to that today, and that's the line x equals a is a vertical asymptote which I'll call VA in this class, if either you're doing a limit at a number, okay, on the left, and you're getting infinite behavior, unbounded behavior there, or if you're on the right side doing a limit, so we call it A plus, and you're getting unbounded behavior. See? All right. Let's go on and talk about just doing some examples where you have to find the vertical asymptotes, and then you have to also find the horizontal asymptotes all in one package. Okay? Okay, can I move the page? Because this next page is just a bunch of examples. All right. So the instructions on this are find the HAs and VAs of the following function. And also describe the behavior of the function on either side of a vertical asymptote. So this matches the instructions in your homework. The only difference between this and the homework problems is the homework problem doesn't ask for HAs. So I'm adding that in, just to review from yesterday. All right, so our first function is f of x equals 1 over x squared. Okay, so many of you remember this graph from Ms. Chen's class as the volcano. Okay, how many of you have Ms. Chen? Okay, so she probably mentioned the volcano. Okay, maybe Mr. Lynch does it that way too. But if you plot this out, what you get is a positive range, because x is always squared, so it always comes out to be a positive output. The graph looks something like this. Okay, that's our graph. All right, so let's write down the horizontal asymptote, if there are any. So it would seem that, it would certainly seem that the x-axis is a horizontal asymptote just by looking at the graph, right? It seems like this thing sort of peters up onto the x-axis on either side. How do you verify that mathematically? How do we know there's a horizontal asymptote at y equals 0? You know, this line. How do you know it's actually there? X cannot equal 0. That explains to me, though, why there is a vertical asymptote here. You see what I'm saying? X can't be 0, so that's not quite the right answer. It's changing pages on me again. Sorry. Wow, stop doing that. Okay, why is there a horizontal asymptote? Yes. So you're plugging bigger numbers in the bottom, what's happening? Yeah, why is it going to get smaller and smaller? That's true. Okay, so what you do on this, if you looked at yesterday's lesson, to verify that this really is an HA, you do a limit as x goes to infinity. And then you do a limit as x goes to negative infinity. Okay, so that's what we're going to do. So we're going to formally show that y equals 0 is an HA. Okay, so why is it an HA? It's because of the limit, not because of the graph. Okay, here we go. LIM, x goes to infinity of 1 over x squared is the limit as x goes to infinity of 1 over x quantity squared. And I had you memorize this yesterday. This inner limit here is 0. Okay, that's our first calculation. The second calculation is to do a limit as x goes to negative infinity. But to be honest with you, regardless of how this next part turns out, we have already determined that y equals 0 is an HA. Okay, so it doesn't matter how this turns out. I already know y equals 0 is an HA. So I'm going to go and record that answer. Y equals 0 for sure is a horizontal asymptote. So why am I even doing this second calculation? Yes, we said yesterday that sometimes you get two horizontal asymptotes, right? So you still need to do both limits. Let's do the left limit. The limit as x goes to negative infinity of 1 over x quantity squared. But I had you memorize that yesterday as well. That also is 0 squared. So it turns out we got agreement on this. Whether you go far, far up to the right, y goes to 0, or far, far up to the left, y goes to 0. One horizontal asymptote. Now we can draw it if we like, because we believe it's there. See? There's your HA. Okay, let's do the vertical asymptotes. So according to the definition, we need to do a limit at a value of x that we believe is restricted from the boundary. Okay? All right, so we are very interested in x equals 0. So let's talk about VAs now. So first thing I always do is find the domain. What is the domain? Well, x cannot be 0. Why? Because my fraction can come out to define. Okay, then I ask myself, are there any x squareds in the numerator that would cancel with this x squared in the denominator? Okay, so look at the numerator. What's my numerator? 1. Do you see any x squareds up there that might cancel with this x squared? No. Okay, again, x equals 0 really is a vertical asymptote. Does anybody remember what it means when there is an x squared up top and an x squared on the bottom? What does that mean? Like it would reduce, like cancel out. That means there's a hole in the graph, kind of zeroing. So it wouldn't be a vertical asymptote. So you look at the bottom, you look at the domain, okay, x cannot be 0, but then you look at the numerator to make sure that that doesn't reduce. This thing is already fully reduced. So I'm going to go with vertical asymptote at x equals 0. Now I'm going to go ahead and check the behavior on either side of it. Okay, so I'm going to do a limit on the left side of 0. And a limit on the right side of 0. Because they asked me to describe the behavior of the graph on either side of the vertical asymptote. That was the instructions. Okay, well the graph, you can see, looked like a volcano. It was going to infinity on both sides of 0. So that's the answer. So we found the horizontal asymptote, and we found the vertical asymptote, and we described the behavior on either side using limits. Okay, let's go to the next example. and that's tan x. Tan x. So same instructions. I'm not going to rewrite the instructions, if you don't mind. Part B is f of x equals tan x. You guys remember that tan x also has vertical asymptotes, right? I have the graphs up here in case you ever need to reference them, but you probably remember the tan x graph anyway. Does anybody remember where the asymptotes are? Pi over 2, negative pi over 2. Okay, and then the period is pi, right? So you just add pi or subtract pi from there. So, yes, you're right. So we have vertical asymptotes memorized, actually, for this. Pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. Right. If you ever forget those, does anyone know how you can figure that out again? Yeah, just think of this as sine x over cosine x, and then you can think of the simpler question, when is cosine x 0? Right? Because whenever cosine x is 0, tangent is going to be undefined. So cosine x would be 0 at pi over 2, 3 pi over 2, 5 pi over 2, also known as 90, 270, 450 degrees. Okay, so you basically can tell that it's going to be these values. All right, and you also remember what the actual branches look like, right? They look kind of like cubics. And they repeat, right? Okay, so those are what they look like. Now let's go ahead and answer the question. So the first question was, where are the horizontal asymptotes? Are there any horizontal asymptotes here? Well, why don't we do a limit as x goes to infinity? Let's find out. So let's do limit as x goes to infinity, tan x, and we'll do limit as x goes to negative infinity, tan x. Okay, neither of these make a whole lot of sense. Okay? As you go out, right, let's say you go out a million spaces, you find one of the branches. If you look at the first part of the branch, it's really, really far down. But if you look at sort of the middle branch, it's right near the axis. And if you look at the right side of that branch, it's at the top, right, way up by infinity. But then we go on to the next branch, well, the same thing starts over again. So with periodic stuff like this, studying the graph of infinity doesn't really mean much. Because what you see out near infinity is what you see here. So there's no chosen y value in any of these branches. It's just like a mess of y values. All the numbers, all the numbers, all the numbers. So we're not going to be able to answer this one at all. This would be a does not exist. Sine, cosine, and tan all exhibit this weird behavior off by infinity. They just repeat themselves. Okay, so periodic graphs don't really have horizontal asymptotes. Unless you like divide them by x or something. Okay, so that part's done. Wasn't very interesting. Let's go to the vertical asymptote case. Okay, so we already said, Hunter remembered that these were at negative 3 pi over 2, negative pi over 2, positive pi over 2, positive 3 pi over 2. I would like to write that a little more concisely. Okay, so everybody pay attention. Lost my page there. How do you write that mathematically? Pi over 2 plus or minus pi. Yeah, that's pretty clever. Pi over 2, if you add pi, you're going to get this one. Would it be pi over 2 plus pi, or 2 pi, or 3 pi, or 4 pi? Okay, pi over 2 plus k pi. Good. Yeah, there's two ways of looking at this. You can say every so we will actually write that because that was your invention. I like it. So it's pi over 2 plus k pi. There's another way to think of it. Instead of thinking of it as, hey, that's pi over 2 plus some things, or minus some things, why not think of it as, hey, every one of these is an odd multiple of pi over 2, right? For example, this is 1 pi over 2, and this is 3 pi over 2. The next one's 5 pi over 2, and then it's 7 pi over 2, 1, 3, 5, 7, like that. And this is negative 1 times pi over 2. This is negative 3 times pi over 2. So you can think of it as odd multiples of pi over 2. That's another way of saying it. Okay, so you can think of it as odd multiples of pi over 2. And in mathematics, if you want to ever write down odd multiples of, you write this, 2k plus 1 times pi over 2. What is 2k plus 1 in math? It is pronounced odd multiples of. Okay, think about it. If x is, the k is 1, that comes out to 3. The k is 2, that comes out to 5. See? So it's like a little sequence. I'm okay with this too. This is perfectly fine. So this is an alternate way of thinking about it. And it's probably what we'll use. Okay, so we're just going to now check the end behavior on either side of the vertical asymptotes, like they said. So we can't do every asymptote because there's too many of them. But here's a sample drawing, right? What happens if you're doing the limit on the left side of one of the asymptotes? So we indicate that with a little minus there. So looking at the left side of any given branch, what's going on the left side of the asymptote? What's going on there? There's the vertical asymptote, we're on the left of it. What's going on? Infinity, right? It's going up. Okay, so that's infinity. And if you're on the right side of any particular asymptote, back to my page here. I wish you wouldn't switch pages on me. I gotta scroll down. It's a lot here. Yeah, if you're on the left side, it's going up to infinity. And if you're on the right side of any asymptote, 2k plus 1 pi over 2 on the plus side of it, what's the answer? So you're supposed to look right here on the right side of the asymptote. What's the answer there? Negative infinity, right? Okay, so we did it. We answered the horizontal asymptotes. It turned out there weren't any. And then we answered the vertical asymptotes. We tried to put it in a nice little closed form. And then we finally answered what the behaviors were like on either side of each vertical asymptote. So the reason I did that example is because the answer is so ugly. If you see it in the back of the book, now you'll maybe understand it a little better. And I think I am going to have time to show you the trick I wanted to show you. Okay? Let's take a look. How about you just give me the next page instead of going backwards when I say forwards? There we go. Alright, so this will be in the video. I can refer period 1 to it if they want to see it. Seeing limits as x goes to infinity. Seeing limits as x goes to infinity. Let's say you're given this problem. You want to find the limit as x goes to infinity of sine 1 over x. Let's say you want to find that. Okay? So you whip out your graphing calculator and you graph it. Alright, let me do that real quick. Sine of 1 over x. Let's see what that thing looks like. We'll just do a zoom standard on it. Okay, a little hard to see. I think I'll make my y values go just between -1 and 1. After all, it is a sine function. And it's divided by a little easier to understand. Okay, so what would you say? We're going way out to the right. What's going on with the y value way out to the right? It's going towards 0, right? You can see that here, right? But can you really see it? Can you really see infinity? You can't really, right? You can't see it. Don't tell me you can see it's going towards 0. How do you know that when you get like way, way, way out to the right, it doesn't like shoot way up high and come back down and then run around in circles? You don't know what's going on here. See what I'm saying? You're right if you think the answer is 0, but I'd like to show it to you, like so you can actually see infinity. You ready to see infinity? Okay, this is pretty cool. I think you'll like this. So since we can't go to infinity, we'll reverse the question. Okay, so we believe it's going like that. I wish this was just a sine x. Okay, I'm going to change this to a sine x. What did I do? I threw away the 1 over x, and I'm just changing it to x. Can I do that? Can I just change 1 over x to x? It depends on what I do with my limit. I'm going to change infinity large to infinity small. I just rewrote the question. What did I do? I took infinity, which means infinitely large and positive, right? And I reversed it to the notion of infinitely small yet positive. This means 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, right? Big numbers. This means 0.0, 0, 0, 0, 0, 0, 0, 0, 0, 0. See? So I'm trading the infinitely large and positive to the infinitely small and positive. And to compensate, I will simply take 1 over x and change it to x, which takes the reciprocal. What's the reciprocal of 1 over something, or what's the reciprocal of something very, very large? Something very small and positive. What's the reciprocal of 1 over x? X. Is this question hard to answer? Not at all. In fact, we can see it. Watch. So I'm going to go like this and graph a sine function, and I'm going to ask you what's going on the right side of sine near 0. It's going to 0. It's going to 0. Go back to that page. We will get a chance to use this again sometime. But what I did was I changed the x, the 1 over x to just x, and then I changed infinity to 0 plus. These are the same exact question, believe it or not. They're the same question. And I prefer the second one because I understand it better.